Hello together. Welcome to today's webinar. The title for this webinar is TwinCAT 3 Realtime Monitor, Precise Diagnostics and Optimization. If you have questions during the webinar, please use the questions window, what you can see here on the right-hand side. We will answer as many questions as possible during the webinar. If these questions would be for interest for more than one people, we will explain it at the end of the webinar, or we will answer if these are more complex questions afterwards. So again, the topic for today is the TwinCAT 3 Realtime Monitor. I would like to start with a short overview why we have created this product. I would like to explain some basics concerning the real time. And I would like to show you which type of markers we could provide for the real-time monitor. I would like to give a short overview about the capabilities of the real-time monitor and how it looks like. I will talk about user-defined processes, and I would like to also show you how to measure with the real-time monitor. And at the end, I would like to give you a short live demo. So let's start with the motivation. So the motivation is split in two parts. The first thing is that we would like to provide a possibility that you could adjust your real-time settings, and you can directly see what is the meaning of these settings and how it behaves afterwards. So of course there are already some specialists who knows each settings in detail and know how the runtime will behave afterwards, but for the most people it's not directly possible to see what the settings or what changes these settings will lead to. And the other part of the motivation is the optimization of processes. So plans become more and more complex, and on the other hand, they must become more modular. And as you already know, we provide with TwinCAT 3 a multi-core runtime environment. And if those of you using these possibilities, which means they have separated and encapsulated the functionality and distributed it to the different core, then it is difficult to become an overall overview about your process and the critical paths and so on. And also this we would like to make visible for you. So let's start with some basics about our real time. Of course, many of you have already seen similar pictures, how our real-time could work, what is the architecture behind. So I have tried to depict it a little bit in another way. So here you can see three different cores, which can be used for our real-time in our real-time environment. And you can see here the TwinCAT 3 real-time kernel. You maybe have often heard about the real-time tick. So in more detail, this is not really a tick, this is a timestamp which you provide for each core. And each of these cores using the same counter, right? And that's why the starting synchronized at exactly the same time. Then on each core in separate, the scheduling for all the tasks occur. And then depending from the cycle time which you have adjusted and for the priority, and the scheduler decided which task is allowed to run. All the TwinCAT modules are assigned to such a task, and so these modules will be called by this task. This is how it basically works. If you look to the execution of a task, then here you can see how a task will be executed. First, what you can see here, the first part is the input mapping. Afterwards, the cyclic update occurs in which we execute your user-defined program. And afterwards, we have the output update. The time for the input update and output update is fixed because the process image is fixed, and this means also the time for copying all the variables is fixed. The only thing what can change here is the time which you need for the cyclic execution. You can see this here, and also here it's a little bit longer. Furthermore, on Windows-based cores, we have a double tick, which means you can define a maximum core limit. For TwinCAT 2, this was 80%, for TwinCAT 3, 90%. And if you reach these limits, we will switch back to the Windows operating system, because otherwise Windows will freeze. If Windows knows a core, you would like to have a little bit calculation time on this core, right? So, and that's why we have this double tick. So, coming back to the execution order here, again, input update, cyclic execution output update. And normally, if you do not have set up this in another way, the EtherCAT frame will be sent out during the output update. And here, if you see this picture, then you can imagine that here the EtherCAT frame is sent earlier than in this cycle, right? Which means you would become jitter on the EtherCAT bus. That's why also under TwinCAT 3, we already provided the version, the possibility IO at task begin. So this is what you can see here in this part of this slide. Again, we have here our input update, output update. Again, both of these parts, the time which we need for these parts is fixed because the number of variables is known. And then if you send out the EtherCAT telegram during the output update, then you can imagine that you have here no jitter on the EtherCAT bus. Also here, we have, of course, our core limit. But we have the possibilities to use isolated cores in which these cores are not known by the Windows operating system or each other operating system. And using this, we have no need to have this double tick here, and then we have, in theory, 100% of the calculation time. Of course, that's not always required, but in theory, you can use 100% of the calculation time. But what happens in case of a cycle time exceeding? Sorry, this is shown on this slide. In the upper part here, you can see only one cycle time exceeding. Here we have the input update and the calculation of your cyclic program, right? And if the core limit is achieved, then we switch back to the Windows operating system, even if the calculation is not done completely. And then we try to execute the last of the calculation, of the cyclic calculation of the first cycle in the second one, and also the output update. And directly afterwards, we try to start the regular cycle, which means here we start with input update, cyclic execution, output update. If this succeeds in time, then everything is perfect. If not, we have the behavior here, what you can see here below. Again, we have here a cyclic execution which needs more calculation time, then we can provide it with the defined core limit, which means also here in the second cycle, we will execute the rest of the first cycle. Directly afterwards, we will again try to start the regular cycle, and also in this case here, we have a cycle time exceeding. And then the behavior is by two successive cycle time exceedings that we not directly start a third try. Then we wait for the next time in which the cycle regularly starts to start again. This is some kind of cleanup. These two successive cycles is also the same if this first cycle needs so much calculation time that it not only needs a second cycle, but also a third one. So it doesn't, it's not important if these are two cycle times exceedings directly afterwards in two different cycles, or if this is one, let's call it big cycle time exceedings, which needs more than two cycles. Okay. Further, we have a difference in the behavior between the execution of a PLC module and classical TC-COM runtime module. This is because we have to be compatible to the TwinCAT 2 environment, right? From this environment, we take the same behavior. And this is what you can see here in the upper part. So each PLC has its own input and output update, and in between the cyclic execution of the PLC. This means if you would like to communicate from PLC 1 to PLC 2 via mapping, then the second PLC or the input update from the second PLC and takes care of the mapping and copying all the information in the input update. And then this means that the PLC 2 has directly the last values from the same cycle. In the other direction, of course, one cycle is lost because then this input updates is grabbing the information on the starting of the next cycle. For classical TC-COM modules, which means programmed in C++ or via MATLAB Simulink or whatever program, these modules will register by a task. This means they register by the input update of the task, the cycle update, post-cycle update, and also by the output update. And this means the task and not the TC-COM module takes care about the different phases of the execution. And this means each input update for each TC-COM module will be executed one after another. And afterwards, the cyclic execution one after another and the output update one after another. If we again assume you would like to communicate from TC-COM module 1 to TC-COM module 2, then you can imagine that you lose one cycle in comparison with the execution of the PLC. Okay? We have to be aware about this difference. Okay, so far for the real-time basic. Now let's come to a little bit closer topics to the real-time monitor. So inside the real-time monitor, we have some mark types to show how the real-time behaves, how the tasks behave. And therefore, we have a sequence start and a sequence stop. And sequence start indicates the time when a task or a user-defined process is allowed to start. This means not that the task also starts the execution due to some not fulfilled requirements or due to a higher priority task which is executed first. The start can be executed later, and this is what is indicated by an interval start or interval stop. And further, we have also the possibilities to use markers if you would like to log a specific event. To make this a little bit clearer, I have this picture here. Again, we start with a sequence start, and this is when the task or the process is allowed to start. And again, due to some missing requirements or due to a higher priority process or task, it does not mean that the task also starts directly, but it can, right? Then the interval start, what you can see here, and the sequence start is there directly overlaying. And then we have here an interval. In this picture, you can see here two intervals inside a sequence. This could be the same process which is interrupted. This would be the example for a real-time task, for example. Or this could also be a big process. So such a sequence can also, for example, depict a complete process which has sub-processes, and then these intervals could also indicate a sub-process. And here you can see a specific mark which can indicate a specific event. So again, here's the mark, then the interval stop, then interval start and interval stop and sequence stop on the same time. Okay, so far for the theory. How does it look like in the real-time monitor? You can see here on the left-hand side some kind of tree structure. Inside this tree structure, we depict context. This could be, for example, real-time context. This is what you can see here. We have for core 0 and for core 1, the real-time context. And it is defined that for a real-time context, if you see all the tasks, which means also the system tasks, only one task at the same time can be active. For user-defined processes, this is another story, but later on more on that. And further, you can see here then, inside this context, you have the different tasks, for example, the idle task, the PLC task, and so on. And this is what you can see here in the middle part. You can see here the execution of the different phases for the different tasks. Here we have our sequence start, then the interval start. For example, for the cycle update, you can further see here the cycle update is interrupted. This is due to a critical section. We have here 2 times the same PLC task and only one EtherCAT, which means both of the tasks execute on different cores using the same EtherCAT. And that's why we have, of course, critical section to make sure that the access of the process inputs and outputs are not danger, and that's why we have critical sections inside here, and this is what you can see here, right? Then you have here the cyclic execution, an output update. Inside this blue part here, ADS will be executed and the sequence stop. Okay, if you directly log in without enabling the detailed view, you will have this picture here with not so much information. If you would like to have more information, you can enable the detailed view, and then you have more information. For example, you can see the input update, the output update, and you can see the part where the ADS is executed. You can see and measure the time which you need for the cyclic execution and so on. You can see here 2 times the same behavior, but here in normal view and here in detailed view. Here the PLC part, task in more detail. I already mentioned the PC task works a little bit different than standard TC-COM modules, right? So you can see here in the, let's call it big green rectangle, the cyclic execution of the task, of the TwinCAT real-time task. And inside this task, a PLC-COM, and PLC module will be executed. And the PLC module has its own input update. This is what you can see here. And the output update, and also underlaying here in the underlaying rectangle, green rectangle, the cyclic execution of the PLC will be shown. So far for the real-time task. The other part of the motivation was that we would like to make user-defined processes visible. For doing so, you can use some specific function blocks which you can use inside your code that you can that you can define marks. Inside this function block, this is an interface call. We provide only 3 parameters, which is the context ID. For these simple marks, what you can see here in this sample, this is always the port number of the PLC runtime module, which is calling this interface. Then we have here a group ID, which defines the process. And here you have an, let's call it event ID, if you would like to have a specific event, what you also would like to provide. This group ID, again, defines the process. So for example, here, you can see here, I have here a sample called conveyor sample, and this is my process 4. I do not have a specific user event here. I would also like to say this process starts here and stops here. So if you have a look on the right-hand side, you can see these function blocks. We have a logmark base, which has a little bit more possibilities, and an additional logmark, which is derived from this function block. And this is a little bit more user-friendly, but has not so much possibilities. And here you can see our sequence start, sequence stop, interval start, interval stop, and logmark. And you can see here a log start and log stop, which is also used here. This log start is in combined sequence start and interval start. So when the process starts immediately with no time in between sequence start and interval start, then you can directly use this log start, which would be the same as if you write here 2 lines of code with sequence start and interval start. So this is similar. And for the most user-defined processes, I believe this makes sense that you directly use this. Again, this time here, the group ID is used to separate the different processes. This is of time uint, which means you can, inside one PC runtime module, have 65,000 different processes which you can display in the real-time monitor. If you need more, you can use this extended function block, or extended in meaning of the functionality, but indeed this is the base function block. And then you can define own context. This could be, for example, if you would like to group your processes in meaning of different process types, for example, transportation or mechanical processes and so on, then you can use this. Or if you would like to separate the processes after runtime modules, then you can also use this. So you can have in context module 1, and in context module 2, and so on. So it really depends how we would like to have it. But for the most cases, I believe these more user-friendly, simple marks, how we call it, will be used. So again, here we have a log start, a log stop, and the same, for example, for my language sample here, and log start and log stop. And in between, I have different log marks because, of course, this is the same process. This is my process language sample. But in between, I would like to have the information when I have a state change. In my case, this was the change of the language which was used here. So I have here a CFC sample and then page-oriented CFC sample and function block sample and so on. And that's when I provide these marks. Of course, these marks have also to have the process in which this event occurs, and then also as uint decoded event ID. This could also, for example, be the state of a state machine. This could be the part number of a specific product which you are producing on your plant, or whatever you need, right? This interface is really simple, so which means you have no strings here available. If you would like to have more information, then you can provide strings to these numbers in the real-time monitor. Everything which has to do with analysis or something like this is completely done offline in the real-time monitor to get this interface as fast as possible. Furthermore, the main difference between TwinCAT scope and the real-time monitor is that in the TwinCAT scope you can grab information only by cycle time, and in the real-time monitor you have an interface which says now, and then we provide a timestamp with the three numbers I already mentioned. Okay, but how does it look like in the real-time monitor? This is here. Now you have here, besides the real-time context, or next to the real-time context, your user-defined context. Again, if you use simple marks, you have here, I have named it PLC, but you have here your contexts which are grouped according to the the port number of the PLC. Or you have here your own user-defined context. This is my unit 1, my unit 2, and so on. This you have already seen. This is my real-time tasks. You can enable and disable these real-time tasks, and here you have the processes. And by this vertical line, you can see which user-defined processes will be executed on which real-time task. This is important for analysis. For example, the yellow process and also the orange process are inside exactly the same. I know this because I have programmed it. So, but as you can see here, the orange process will directly execute it, and the task which will be which will execute this yellow process here is interrupted. And that's why if I measure the time for the processes, I will see later on, okay, that's why the yellow process, even it's exactly the same like the orange process, will need more time. Further on, I already mentioned, plants become more and more complex, which means maybe the complete process will be executed on different runtime modules. And so you can see which part of your complete process will be executed on which core, on which task, right? And that's why you can get the information about the critical path of your complete process, and you can do some adjustments in the execution order or whatever, so that the process will become faster, which means afterwards you have more outcome of your machine or plant. How to measure something? In the real-time monitor, we provide cursors. You can have as much cursors as you want, and you can move the cursors inside these windows by using drag and drop. And you can see here the different marks. And if a cursor is nearby such a mark, it will directly jump on this mark, so that you do not need a concern about that the times will not equal each time. So it directly, if it's nearby, it directly jumps to these marks, and then you can measure correctly. This is what you can see here, and you can see here you have some kind of table between the different cursors, so you can see, you get here the numbers in between, in meaning of the time between the different cursors. And for the active cursor, this is here in this picture, cursor 1, you can have here on the right-hand side all events which occur in this time. So you can see here, this is cursor 1. You can see here you have some event in the PSC task on core O and PSC task on core 1 and the 2 processes here, right? And this is what you can also see here. So Untitled 1 will be executed, PSC task 2 starts executing, and also for the counters we have an interval start for the first one and in sequence start for the second one. Okay, you can see this here. But maybe it's not, or if you imagine you run not only one cycle and you would like to have some kind of statistics, what is the typically cycle time or other cycle time exceedings, and therefore we have the possibility to create a statistic over the complete time you have measured. This is what you can see here. You have here an overview about a complete core, but if you click on a task, the graph type here will change. So then you have some kind of bar graph, and you will see some Gaussian curve which show you the different execution times. But later on more on that. Okay, now let's come to a live presentation. I have prepared a TwinCAT project. This is our fair demo project, which you maybe know from the different fairs on which we show our TwinCAT system. I have here used here in this sample the simple marks. You can see here an instance of this, let's call it simple function block. And I can use the same instance here for measuring all the different processes. What I have to provide is what kind of mark is it, log stop, here in this sample, or here if it's a mark. You have also seen this on these slides before. And I have to define which process it is by providing the group ID and which event I would like to have here by this event ID. Okay, and you will see this later on in the Realtime Monitor. I mentioned we have also some more complex marks. This is here our log mark base. And by using this, you have to define the marks by your own. This is what you can see here. This is our mark. Then you can define a context. Again, this is some sort of grouping. This could be, for example, a module or type of process or whatever you would like, in which way you ever would like to group your processes. And then you have here the group ID, what you also have seen in the simple marks, which is basically the process. And here the event ID, which you can use or not can use. And then you have a bit array, which defines what type of mark is it. Of course, we have prepared everything so that you can directly use specific options here. But you have to combine these options by your own. So by using the simple mark, this option here, ref to color, is always active. This option will be used to depict these vertical lines, which shows the assignment from processes to real-time tasks. And here's the option start, which is similar to the log start option from the simple marks. Okay, now I would like to activate this project. Of course, I have changed something in the configuration so that the configuration is not optimal. Otherwise, it makes not really sense to show you something which runs perfect. So I will activate the configuration here. I will start the PSC. Okay. And now the PSC will be executed. And now I will open the Realtime Monitor. Okay, here we are. I will start with creating a new project, and then I can directly connect to the target system I would like to measure, from which I would like to grab information. In my case, it's my local target system. And then I will be asked if I would like to load the configuration. Yes, I would like to. And if I would like to search for user context, I would also like to. search for user context, and then I get here the information that I have two cores. I have obviously I have in motion active, I have a PSC fast task, and on the other core I have also a PSC task, an IO idle task, and so on. So these are the user contexts here, and now you can manually, for example, provide more speaker names. If you have done this once and it's always the same for your different plans, or you will use later on always the same IDs, then you can export all your settings and you can import it later on. That's what I have already done. So I will import my user-defined context. So these are basically these two. So open here we go. This is the PSC, I already mentioned this, and now the different processes. And also my user-defined context is available here, and so on. Now I can specify if I would like to see the task reference or not. This is switched off by default. Otherwise, if you have really a lot of processes and also, a lot of tasks and so on, you have, of course, a really colorful picture, but it makes no sense in meaning that you could really see something. So that's all for the user processes. Now you will see everything. And for the real time, you can also define if you would like to see all the system tasks and if you would like to see really detailed information. So I've activated everything. So what you now see here, if I activate everything, is not really starting of measuring. If we connect to the target, we scan shortly the marks. I mentioned already that each kind of analysis is done offline. So we start measuring really a short time, only a few cycles, and stop it directly so that we can grab all this information here. And that's what you can see here. And because of detailed logging was not on, you does not really get deep information. So the regular recording starts now. So only a short time because I will create a statistics afterwards, and this should not take too much time. But you can see here the Windows slice. This is what you can see here. Core O Windows and Core 1 Windows is active a lot of time, which means I have a lot of free calculation time on my target system. So, but that's not what I would like to see. I would like to see how the real time behaves. So this is what you can see now. I can make it a little bit. I do not have a mouse here on my laptop. So here we go. You can see here, obviously, we have two PSC tasks. Here's the IO idle task. And here in this part are our user processes. Okay? These two processes will be executed in parallel. And we have here some processes which will execute one after another. You can see my language part with the different marks in between. Okay, now we would like to have some more information how the real time behaves not only in one cycle, but we would like to see how it behaves in multiple cycles, right? So what you can do, of course, you can, by using drag and drop, you can browse through the complete process, or you can use our triggers. We have here, for each task and also for each process, we automatically grab which marks are existing. So for example, for the PSC task, I would like to see each sequence start. This is this one here. And now by these two green buttons, I can manually browse to the process. So what you can see here, the behavior is different between the directly successive cycles, right? If you look closer, then you can see here, the input update and output update will not done by PSC1, but PSC2. So, and the reason why this behavior is different is we have here the NC fast task, which is active in this cycle, but in the next cycle not. So, and this leads to, so again, I do not have here an EtherCAT because I'm on my laptop here during the webinar, but if I would have here also an IO device, an EtherCAT, then the output update here will be executed here in this PLC. And that's why I would have jitter. Each successive cycle, I would like to have a different execution time. This is what you directly can see here in the real-time monitor. Further, you can see for each task here, the priority. If you click on a task, you can see here the priority, the object ID, the alias port, and you can see here also the meaning of the different colors. So, if we would look later on a little bit deeper in this program, then we would see that I also have the NCSVB task, which has a higher priority. The priority of this is 8. The cycle time is 10 milliseconds. For the fast task of the PLC, the cycle time is 1 millisecond, and the priority 21. And this means if you do an analysis later on, you will see that on each 10th execution, you will have here maybe a cycle time exceeding of the PLC fast task. This is also what you would like to see here. Further on, you see here directly that the IO idle task has a higher priority than the PLC task of the second core. So for those of you who already know this, the IO idle task will be used for the background communication. For example, from the engineering environment to the target system, but also for grabbing the information from the real-time monitor, and also if it has parameter communication between the different I/O terminals. This is all done by the IO idle task, and this means as soon as you measure something with the real-time monitor, you will change the real-time behavior, and that's why it does not make sense to have the IO idle task higher priority than the PC task. This is only really a few cases when it makes sense that the IO idle task has a higher priority than the other real-time tasks. So this is also what you would like to change maybe afterwards. Okay, this is all what you can see. Of course, you can not only manually use manual triggers, you can also use a trigger from the collected data. Then from all the data we already have collected, you can see it here. Or you can also use live data. So in differentiation to the scope, we do not have an real-time monitor server on the target. That's because of the real-time monitor really produces a lot of data. Because if you imagine you have such a 12 or more core system, then you can imagine that we really have a lot of data if we have also fast cycle times. That's why we only grab data if we are connected with the real-time monitor, and the complete storage of the data will be done by the real-time monitor on the engineering system. So, but maybe you would like to have some information in case of a specific event, then you can, by using this live data trigger and defining here a trigger prelude, you can define how much forecast to a specific event you need in maximum 1 minute. And then you can do your analysis. If a specific occurs, then all the information will be stored and you can do later on an offline analysis. Okay, so far for this. I mentioned that we can do we can create a statistics that I would like to show you now. Now the statistic is created. We have an overall overview about each core. You can directly see, okay, Windows has over 90% of the execution time. Again, that's why I have a lot of free calculation time here. I can do an analysis only from one core, but what is more important is a specific task, for example, the PC task. I mentioned that you have some kind of Gaussian curve here for the different execution times. You can see here the separate execution times which was measured, and also the number of cycles in which this execution time will be achieved. So normally, this execution time here will achieve, but if I zoom in here, you can see, oh, we have also here some higher execution times. But I would like to see exactly when this happens, right? Because this could be a cycle time, or this could be the reason for cycle time exceeding. Then, if we have a look here on this timestamp, if I click on this, then this timestamp should change to the latest cycle in which this cycle time occurs, and then I press here jump to and switch back to the chart, and I'm exactly on the location when this cycle time exceeding or whatever occurs. So that's how you can do analysis. And you can of course do the same also with user processes, right? We not only create a statistic for real-time processes, but also for user processes. Here, for example, you can see 2 times a Gaussian curve, and that's because of what you have seen, right? We have a different behavior because of the motion times, because of the motion times task, which will be executed only in each second cycle. And that's why sometimes you will have this execution time and sometimes you will have this execution time. And you can see this all here in the real-time monitor. Okay, so far for my live demonstration. To sum up a little bit, by providing for you the real-time monitors, we have a tool which allows to display the scheduling and the timing of our real-time system, and only in really detail the task processing, which means you can see the sequence start, input update, and post-cycle update, and so on. You can see this. Furthermore, you can also see the interaction of the different tasks on the different cores. You can also see the transmission time of the EtherCAT and how long these telegrams are. And you can use this to display your user-defined processes and events to become more familiar how your process really behaves with the setting you have done. Okay, what's the question so far? The first question is if there is a way to export the real-time monitor recording. Yes, we have. I will switch back to the real-time monitor and show you shortly in more detail real-time monitor webinar. Oh no, I do not have stored it. Basically, we have 3 different storage formats. The storage format CTX provides this information here, what you can see here, which means the number, the context IDs, and the process IDs, and also the colors you have used. Then we have an RTM file, which is the real-time monitor project, which do not provide you this information here, but all the information is here, which means which tasks you have, and so on. And we have a .data file, which contains this information. So if you would like to provide someone the information, you need to provide them the RTM file, which is the project here, and the data files. These are separated. So this means if you only provide somebody a configuration of the real-time monitor, you can provide them an RTM file, and then you can press the play button. If you would like for analysis to provide everything, then you have to provide the RTM file and the data file. Oh, okay, then no more questions. So I hope this was clear, everything. If not, you can write us an email by using this email address. Sorry, go to webinar.beckhoff.com. If you write us an email, we will answer this question, all your questions later on. So then again, thanks for attending this webinar and have a nice day.